Hello and welcome to Aerospace and Mechanical Lab 1. Today we are going to discuss the second lab of the Lab 1 series. The second lab has two parts. One part is an analog measurement of bending and torsion done using this arm-filled apparatus. And then the second part is the digital measurement of deformation, strain, and force that is done through a strain gauge and a load cell that is pre-installed on the machine. The idea is you guys start learning about different types of measurements in the lab. We are going to start with this one. I'm going to show you how to do this, and then we're going to move to the next lab. Okay, so let's start with the bending test first. For the bending test, we have three different beams. They're essentially the same material, but they have different cross sections. And one is an I-beam, one is a hollow beam, and one is a solid beam. And you are going to essentially install them right here. I will only install one and show you how to change the support. You want to make sure you actually have this in the middle so you can start adding loads. I'm going to use the solid beam, but you have to do this for all of the other beams as well. The solid beam needs to be installed on its vertical end, okay, on the narrow side of it, I'm sorry. Okay, so we have installed it right now. And one thing you want to do is to change this dial to 0. You have to rotate it to make sure the value that is reading right now without any loads is 0. And I want to actually fix this support. Again, the first part of the experiment is to do fixed support experiment. This changed my dial, so I'm just going to move it again to make sure it is on 0. And then this dial is going to give us the deflection. First thing I want to do is to add a little bit of weight. This is 50 grams of weight. And then we are going to add weight to our measurement. This is 20 grams of weight. Another 20 grams of weight. Let me actually add a lot more weight. So right now we have a total of 130 grams of weight. And this dial has moved just a little bit, 0.02 millimeters deflection. And we're going to keep doing this. We're going to record this data, and we're going to keep doing this a couple of different times. You can actually add more weight so you can see more deflection. And when you actually record all of this data, you can compare the deflection for each beams, which is going to give you an idea of how important is the moment of inertia. And eventually, you're going to use all of this data together to give us an understanding of what is the modulus of elasticity for this beam. But so this is for the fixed support, though. We have a couple of different conditions. You need to change the beam. You need to use these two different beams as well. And you also need to change the support. Right now, we are at fixed support. But if you loosen this support a little bit, you are going to be, as you can see, the deflection changed radically because we are not at fixed support anymore. We are at simply supported beam, meaning that we can have rotation as this support. So essentially, you do this experiment once with fixed support, then with looser supports, then you change the beam. You are going to do the experiment 6 different types for 3 different beams and 2 different support systems. The next part of this experiment is about torsion. Torsion will be done using these rods. One is a field dot rod, which is right here, and one is a hollow rod. Again, the idea is to find the modulus of elasticity and compare the angular deflection that we're going to see for the hollow rod compared to the field dot rod. This is how you actually install your rod. You want to make sure that these supports are very, very tight in place. The reason is we want to make sure we actually do not see any slippage. So make sure that your supports are tight, as tight as possible. And then to measure the angle, we have two different devices. One is an analog, very simply, just simply put it on this side and measure the angle as this moves. Or we can use this digital angle measurement system. This connects magnetically to our arm. Right now I'm reading a value of 3 degrees. I'm just going to add a bunch of weight to it. I can zero the 3 degrees by just pressing the turn on button once. I'm going to add a little bit of weight. This changed to 2 degrees with 50 grams of weight. I will add a little bit more weight. Change to 4 degrees with 20 more grams of weight, and so on and so forth. So this is how you do this experiment one time. Then change the rod to a hollow rod. Do the experiment another time. Compare the thetas, the different thetas for the two cases, and then you use all of this data to calculate a modulus of elasticity with a confidence interval of 90 or 75%, whatever we have asked you in the lab memo. This part of the lab is done. We have to move to the digital part of the lab now. The second part of this lab is dedicated to a strain gauge that is installed right here on our device, and a load cell that is installed underneath this dial right here that we have. And the idea would be to measure the strain right here, measure the force that we are giving right here, and then use the two to find the modulus of elasticity of this beam. You want to make sure you actually find this length and the thickness of the beam. All of the measurements needs to be done for you to actually relate the force to here, convert the force to a stress at this specific point, and we already have an equation that relates the stress at this specific point to our strain using the Hooke's law, right? So the device is set up right now. As you can see, we have, again, a strain gauge already installed, load cell already installed, and all of these is connected to our DAQ. This is a DAQ that has the card reader and also the card itself. And the strain gauge, I think this is the strain gauge. The strain gauge is connected to one of the channels. The load cell is connected to the other channel. But we need to know the channel number. The way we read the channel number is from here. You see a number right on the top. It says NI9219. And then you start reading from here, 0, 1, 2, 3. So strain gauge is installed to channel 3. Force load cell is installed to channel 2. Okay. Now how we can set this up is through a Signal Express software. I'm going to open the Signal Express and set this up for you. You can follow me during the lab. Empty Signal Express project. This is what shows up. In order to read the strain gauge, we have to start here, add a step. We want to acquire a signal, so the first option, and the signal we're acquiring is through a DAQ. This is a DAQ of interest. And then a stress signal and force signal are analog signals. When you open this, it gives you a lot of options. One of them is a strain. Let's click on the strain. That is asking us about the channel that we actually have to choose. We did count the numbers. A strain is installed on channel 3. The one thing you need to set before running the experiment is the correct values for gauge resistance and gauge factor. It is usually already set up to gauge factor of 2, which is the value we are going to keep. Gauge resistance is usually defaults to 350. The resistances we have here are 120. They have the 120 ohm gauge resistance. But the most important part of the setup is this. The strain configuration usually defaults to full bridge. You want to change this to quarter bridge 1. And then the next step is to do the calibration to make sure the 0 value for a strain corresponds to the correct 0 value for voltage. There is nothing you need to change here. Hit next. And then the strain is going to be measured. As you can see, we are given 49% error. I'm going to hit calibrate. And the error dropped to 0.018. So this is the unacceptable value. Next part is to add the load cell. I'm going to hit the plus sign here, go to force. This is again a bridge configuration like the strain gauge, and it is installed on the second channel, 0, 1, 2. We don't really need to change any of the settings right here, but we do need to calibrate the device. %23 error. I'm going to hit calibrate again. So the calibration is done. What I'm going to do is I'm going to change this to table, and then this is going to be my strain. This is going to be my force. I'm going to apply my force. I'm sorry, you have to start running the program, of course. So let me actually unload this, run the program, and we are ready to load our load cell. So you can see for the value of 29 or 74, I did change to 74, we are reading a value of 250 micro strain. There's a U here, that means that this is micro. And a strain is unitless, so this is 247 multiplied 10 to the power -6. But you want to keep that in mind, that this is the value of force that you read is 100 times greater than the value you should see. So for 1 pound of force, we should definitely see around 330 micro strain. The value is 97. Again, if you see a value 97, you have to divide it by 100, and that will give you a value of force in pounds, and the value of a strain can be used. So what you do is you need to record at least 5 data points. So as long as you confirmed for 1 or 100, you get 300 and something micro strain. You are ready to take the other measurements. Again, add load to this, read the strain value, and this will be the values you will use for your calculations of modulus of elasticity of the beam. When you're done with your data recording, make sure that you actually unload the load cell and stop the recording right here and close the program. And that will be it for today's lab. See you all next week.